Okay, so thanks, Michel, for the presentation. I'm Tommaso Alberti, and I will present a work I made at the beginning of my PhD in 2014, which refers to the investigation of paleoclimate variability by using a nonlinear time series methods, which is called empirical mode decomposition. And this is the reference for the paper, and this is the outline of my talk, just a brief introduction about the climate variability, and then I will show you how the empirical mode decomposition works, and then I will show you the results we obtained. And as you know, the Earth's climate presents a variability over different time scales, both on time scales and spatial scales. It is a nonlinear complex system which is characterized by different interaction between different components, and by analyzing different both observationals and reconstructed records, it has been shown that there are several scaling features in this time series with different spectral and scaling slopes. For example, by investigating the hemispheric temperatures has been found a scale invariant properties over a slight range of scales, and moreover, also, this scale invariance has been also observed by proxy temperature and by different reconstructions obtained from, for example, for ice cores, which has been presented by Michel in this morning. And the most important feature is that there is a variability between glacial and interglacial climate, and this variability seems to be different because the scaling properties of a glacial climate period is completely different with respect to the interglacial variability. As shown, for example, by Shao and Dietrefsen in 2016, there is a difference between the current interglacial period, which is the Holocene, which manifests a monofractal behavior, with respect to the last glacial period, where an evidence of the multifractal behavior is observed. And one of the most probable cause of this multifractal behavior could be the existence during the last glacial period of the so-called Dansgaard-Eschger events, which are fast global warmings which suddenly occurs during the last glacial period, and this could, due to their intermittent light behavior, this could produce a multifractal spectrum. So our work was focused on this type of events, and in particular we focus on two different time series related to the North Greenland and to the South Pole ice cores, in particular to the Delta 18 oxygen isotope as presented by Michel this morning. And these are the two time series between 20 and 120 kilo-year before presence. And you can see here, for example, referring to the Northern GRIP project, fast global warming events, which are the so-called Dansgaard-Eschger events, which are not so clear visible in the records obtained from the South Pole. And in order to investigate this timescale variability, we use this technique, which is called the empirical mode decomposition, which is an adaptive and a posteriori method, and which works, as you can see here. Assuming to have this type of signal, you need to identify both local maxima and minima, and you need to interpolate these maxima and minima by using cubic spline interpolation. Then you evaluate the mean envelope and you subtract from this time series. In this case, the example is simple because when you subtract this, you obtain an oscillating component and a residue. But in general, this procedure, these 4 steps, needs to be repeated more time to extract what we know as intrinsic mode functions, which are this type of signal, which need to satisfy 2 different properties. One is that the number of zero crossings must be equal or differ at most by 1 with respect to the local maxima. And another one is that the local average must be 0. So you need to iterate this procedure a lot in this case is so simple, to obtain the different oscillating component. And in this case, you can write your time series as a sum of finite empirical modes or intrinsic mode functions plus a residue of the decomposition, which is a non-oscillating function. And the great property is that by using the so-called Hilbert transform, which is defined like this, you can write these empirical modes as modulated both in amplitude and in phases. This is one of the most interesting properties of the empirical mode decomposition because as a time-dependent amplitude and frequency or phase with respect to fixed amplitude and frequency, for example, for Fourier or wavelet analysis. In this case, you are able to follow the non-linearities which are present in your time series, while you are also able to follow your non-stationarities because your frequency is time-dependent. So you have a more information about, more local information about your time series, and you can also define the generalized Hilbert power spectral density, and in the case this Q is equal to 2, you obtain the so-called Hilbert marginal spectrum, which is exactly the counterpart of the Fourier spectrum. But it is obtained by exploiting local properties of the signal, and these are the results. For example, applied to the South Pole record, we obtain 15 empirical modes, this one plus the residue, while for the North Pole record, we obtain 17 empirical modes plus one residue. But what is interesting is that if we plot, for example, the information contained by the Hilbert marginal spectrum, we obtain a different scaling law. This scaling law has been quite identified by Lovejoy and Scherzer, which they associated to the macro weather scales, the climate and the macroclimate. The macro weather is not suitable to be investigated by this type of data because the resolution is larger with respect to the typical time where macro weather processes occur. So we concentrate on the climate and macroclimate regimes, and in particular we operate two different reconstructions by selecting empirical modes with time scale, mean time scales in this frequency range and in this one. And for example, by using the South Pole records, we reconstructed 4 empirical modes to obtain these reconstructions of modes, and the other 6 modes to obtain a large-scale reconstruction. These represent the variability associated with the climate timescales, while this one to the macroclimate timescales. And the same reconstructions have been obtained for the North Pole records, and here are clearly evident the Dansgaard-Eschger events, and indeed, if you try to superpose your reconstructions to the original time series, you know that the red line exactly matches the occurrence of the DO events, and this can be used to obtain time series which are related to different climate or macroclimate regimes and two different time scale dynamics. So one of the main advantages of the empirical mode decomposition is that it could help to detect DO events, but also to investigate and to reproduce variability on different time scales. And this could also be useful for example, for synchronization effects or also to correlation studies between North Pole and South Poles. But another interesting thing we found is that if we try to describe the two different timescale variability by using a one-dimensional Langevin model, those equation is, as you know, this one, we can derive the associated Fokker-Planck equation, and by searching for a stationary solution, we can derive the potential function as dependent of the logarithm of the observed probability density function. And if your potential function can be written as a polynomial, the degree of the polynomial is related to the number of the climate states you have. In this case, is 1/2 of the maximum degree of the polynomial. And what is interesting is this one. If we evaluate the potential function for the short-term reconstruction, which are able to reproduce the Dansk-Kardashev events, we know the existence of a single well potential function, which means that we have only one climate state, while if you look at the behavior of the potential for the long-term dynamics, this is a clear double well potential function, which means that here we have two different climate states. How we can interpret these results? These results can be interpreted in terms of the switch between periods in which warmer or cooler events are found on longer time scales, and the jump between one to the other well could be also associated with the occurrence of the O events, which need to be seen as fluctuations within each well of the larger timescale potential function. So the Dansk-Kardashev events can be not only interpreted as noise-induced transition, but also as physically related processes which occur inside a single state potential function with respect to the longer timescale dynamics, which represent the switch between stadial and interstadial periods. And these are the two main conclusions, and we are also looking for applications of the empirical mode decomposition to the Pleistocene climate with Peter Didresen, and we are looking for an interesting behavior between, I think Michel is very expert in this, between the difference between 41 kiloyear world and 100 kiloyear world, because the empirical modes are modulated in amplitude, so we are looking for checking the occurrence of frequency locking phenomena. And this is just the first application we made in the paleoclimate records, but we are continuing in this way also regarding, for example, the scaling features of the last glacial period. And thanks for the attention.
Thank you. We need to talk. Questions? Okay, I'll try one in that case. You started the talk by referring to this multifractality, or maybe supposed multifractality. Again, we can talk more. We won't do a full chat now. But how is your inferences with the Hilbert, well, the EMD, how does it dialogue with this idea of multifractality?
Yes, this is one of the work we are carried out. By using this formula, I will show you.
Yeah, that was the one, yeah.
This one is the generalized Hilbert spectrum. So you can obtain information at different statistical moments. And by looking for different statistical moments, the most important thing is that you can investigate scaling law in different timescale regimes. And so you can use this generalized function in different timescale regimes to obtain different scaling exponents. So you can free to obtain different multifractal spectra.
Okay.
But there is also another interesting thing, because there is, I think, for example, Shaw and Didresen applied the multifractal determinant fluctuation analysis, which is based on structure function. There is a useful technique based on empirical mode decomposition through which the structure functions are evaluated by using local extrema. In this case, you have not to fix a priori your time scale, your scale over which evaluate structure function, but it is fixed by the different modes. We apply it to solar wind turbulence. It is very useful, and we are trying to apply also to this if you want.
Okay, I'm looking forward for the chat.
Yes.
Other questions? In that case, it's fine. Thank you again, really, and thank you for keeping on time.